what do we have? A relative max is going to occur when the function switches from increasing to decreasing, or when the first derivative changes from positive to negative. That's what our first derivative test says. We can use the first derivative to decide whether or not we have any relative max, relative min, or neither. Well, the first derivative changes sign from positive to negative, which means I'm going to have a relative max. Right there, at x equals -2, I have a relative max. Why? Because f prime switches or changes from what to what? From positive to negative. That's what I need to see. Do I have a relative min? Yes, I do, because I'm going down and back up. So I'm going to have a relative min right here at x equals 1/3. And why do I have that? Use your first derivative test. This is because f prime is switching from negative to positive. Negative to positive. This is my first derivative test. And all of these could be answers for something. Let's just say they're all answers for what I want you to do. So even though I didn't give you any directions at the beginning, this is what the question wants you to do. I don't know if they're going to ask you for a relative max or a relative min, or to give the increasing or decreasing intervals. Always give parentheses around your intervals, okay? Make sure you do that. On the AP test, they will not look at your chart whatsoever. They will not even consider glancing at a sign chart. So therefore, when you tell them where the function is decreasing or increasing, you must follow it with the reason. The first derivative has to be greater than 0 to have the function increasing. The first derivative has to be less than 0 to have the function decreasing. When you take a quiz or test with me, you'll get points for this, you'll get points for this. You'll get points for this and this and this and this and this and this. Okay, so you have to be super careful. And yes, this is my nice first derivative test. I really like it, but don't forget, my favorite is the second derivative test. All right, I'm going to give you one more example as quickly as I can. I know this is lasting longer than it needs to, but you can always stop your video, come back to it another time, or you can fast forward to wherever you need as well. All right, so here's my second example. I pretty much can leave all of that. I'm going to switch my intervals. I know I'm going to have a whole different chart, but my labels are going to be the same. And of course I want to get into something with a little oomph. I don't want to insult your intelligence and pretend that you can't do anything harder than a nice polynomial function. So let's get into something a little tougher. Let's do f of x equals, we can call this example 2. I don't think anywhere on the first example I wrote example 1, but we can still do this. F of x equals x squared minus 2x, I don't like that squared, x squared minus 2x plus 1 all over x plus 1. All right. So we're going to find where the function f is increasing and decreasing, and whether they have any relative max or mins. So any relative extremas. Okay, now what do we notice about this function? You should notice something. This function is definitely undefined when your denominator equals 0. X equals -1 is going to make that denominator equal 0. So we care about that. We want to know whether or not maybe x equals -1 is going to make the numerator equal to 0 too. Because this might be a vertical asymptote, because it makes it, x equals -1 makes the denominator equal 0. It might, however, just be a whole, and we could factor it out. But let's take a -1, and let's just see what we get here. -1, if we square it, -1 squared minus 2 times -1 plus 1. My question is that going to equal 0? When I square -1, I get 1. -2 times -1 is like +2 plus 1. That gives me 4. I don't get a 0. Okay, so something I know is that x cannot equal -1, and I am just going to say that I have a vertical asymptote at x equals -1. I'm just going to put that in there. I have a vertical asymptote at x equals -1 because -1 makes the denominator equal 0, but not the numerator equal to 0. All right. let's see where we're going. I need to go ahead and take the derivative, find some critical values here, some critical numbers. That's not so bad. We have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Or what you guys like to say, low to high minus high to low all over low, low. So, don't forget, I want this notation. Please, if you're going to take a derivative, tell me you're taking the derivative. Okay. Let's see where I am. Let's simplify this down a little bit, multiplying it out. Hopefully I'll get some terms that will cancel out and make this thing nice and neat a little bit. So I have 2x squared minus 2x plus 2x minus 2. Make sure I didn't do that wrong. And then I'm going to distribute this negative, minus x squared plus 2x, and then minus 1. All over x plus 1 quantity squared. Well, this is a really nice pair of something right here. Saying goodbye. Bye-bye. And then 2x squared, take away x squared is just x squared. And then the only x term I have is a plus 2x. And then negative 2 minus 1 is negative 3. All over x plus 1 quantity squared. Okay. So let's take a peek at this. Find our critical numbers. Well, our denominator equals 0 when x equals negative 1. So when x equals negative 1, f prime is undefined. Now, it would have been nice and neat if I had said, let's get rid of some of this chalk right here. If I had put this a little bit neater and said the function's derivative at negative 1 does not exist. That would have been a nicer way of saying that. Quicker, sweeter, more accurate, or just as accurate, just nicer. Okay, so is negative 1 going to be a critical number? Was negative 1 defined in the original function? No. And if it's not defined in the original function, then negative 1 cannot be a critical number. So x equals negative 1 is not a critical number. And that's because f of negative 1 is undefined. So let's take a peek and see whether or not I'm going to ever have a critical number due to the fact that the first derivative is equal to 0. We're going to get a first derivative equal to 0 wherever the numerator equals 0. I'm just going to use this little space right here, copy the denominator, and I'm going to factor this. X, x. I'm going to have two different signs. The bigger one's positive, so plus 3 minus 1 should be my correct factors. That should give me two critical numbers off the numerator. So if this numerator were to equal 0, x equals negative 3 would be a critical number, and x equals positive 1 would be a critical number. Those are the two critical numbers that I'm going to have to play with. All right. So I have my number line up here, and I'm ready just to grind out this chart and answer the questions. I think the rest of this is a real simple task, actually. Build the intervals around any discontinuities and any critical numbers. Well, do I have discontinuities? I do. At x equals negative 1, I have a discontinuity. Do I have critical numbers? I do. Negative 3 and positive 1. So I have 3 spots on my number line here. So what's the lowest one? Negative 1, negative 3, or positive 1? Negative 3. What's the biggest one? Positive 1. So therefore, the one in the middle is negative 1. So I'm going to build my intervals. Pretty simple to do once you put them on the number line in order. So I'm going to go from negative infinity, open parentheses, negative infinity, all the way to negative 3. Draw a line. I'm going to write x equals negative 3 here. And then I'm going to go from negative 3 all the way to negative 1. I'm going to draw a line, put my negative 1 in here. And then I'm going to go from a negative 1 to a positive 1. And draw a line, put my x equals positive 1 right here. And I'm going to go from 1 to positive infinity. So notice I put 1, 2, 3 numbers on my number line, and I have 4 intervals. You're always going to have one more interval than you have the number values on your number line. So, not including your infinities, but whatever you have to plot on your number line. All right, test points. Let's do this. negative 10. Give me a number between negative 3 and negative 1. Negative 2, 0, 10. You okay there? Where do I like to put my test point into the derivative? I'm certainly not going to do it way up here. Not going to do it here. I'm not even going to do it here. I'm going to do it in the easiest factored form that I can come up with. Okay, so I'm going to take a negative 10. I'm going to have a value on the top times a value on the top all over. And isn't that denominator always going to be positive no matter what I put in? Add 1 and square it. I'm always going to be positive, so there's no sense in even testing there every time. So I'm just going to set this up. I have 2 factors on the numerator divided by a positive. 2 factors on the numerator divided by a positive. Negative 10. Negative 10 plus 3 is negative. Negative 10 minus 1 is negative. So this is negative, negative. This gives me a positive answer, which is greater than 0. Tells me f of x itself is increasing. Draw a little line going up. Negative 2 is my test point. If I put a negative 2 here, this factor will be positive. If I put a negative 2, that factor will be negative. Positive, negative. I only have one negative sign, so this is negative, which is less than 0, which gives me decreasing, going down. Okay, increasing, decreasing, increasing, decreasing. You think so? Let's give it a try. Let's put a 0 in. I put a 0 here. This gives me positive, this gives me negative. So I have positive now and negative. I only have one negative sign, so this is negative. So I'm still less than 0. It didn't switch to greater than 0. This is still decreasing. We've seen that a function can decrease, level off, and decrease some more. And it certainly can. Okay? Especially if we have some kind of a x equals negative 1. That wasn't even a critical number, was it? That was a vertical asymptote. So the function is going to decrease near the vertical asymptote, and then from the vertical asymptote, decrease some more. Anyway, we know that isn't going to work. So we have a 10 here. 10 plus 3 is positive. 10 minus 1 is positive. So we have positive, positive, everything is positive. That's greater than 0. So all of a sudden, I'm increasing. Again, this is your theorem 3.5 that allows you to tell whether or not you're increasing or decreasing based on the first derivative. However, the first derivative test lets you determine whether or not a function has a relative max or a relative min, depending upon whether the first derivative changes sign from positive to negative or negative to positive. Okay, let's answer our questions. The function f. The function f is increasing. Where are we increasing? Let's see, where did I write increasing? Right here. Okay, so negative infinity to negative 3. I wrote it again someplace. Where was that? Right here. From 1 to infinity. And why is the function increasing on those values? Because the first derivative was positive. This is because, I put because, f prime is greater than 0. Where are we decreasing? Decreasing where? Let me see. From here. Let me see. Negative 3, negative 1. And then again, where did I write decreasing? From negative 1 to 1. You cannot connect these. You cannot connect these. Don't say from negative 3 to 1. You have to have that separated. You can't decrease across a vertical asymptote. Can't do that. This is because why? F prime is less than 0. This is the reason for increasing every time. This is the reason for decreasing every time. So the function f is increasing. I'm going to write is, take is away and say has a relative max, has a relative min. All right, relative max, my first derivative test. First derivative, if I want a relative max, I have to change from a positive slope to a negative slope. Okay, do I change from positive to negative anywhere? Look, right here, positive to negative. So the function is going from increasing to decreasing. It's going to go through the max. That makes sense. Increasing to decreasing has to go through this max. And the critical number is definitely defined in the original function. So we're good on that. Okay. So we have a relative max at x equals, what is that? Negative 3. And why is that? Let's use our first derivative test. we have a relative min